Yeah, here we go. Well, hello everybody and welcome. It's Mr. Bray sitting here in my home office. I got my trusty Batman cup. I'm ready. Let's do this. So for about the next hour and a half, we're going to be going through the in-class Regents, the first one that we took. This was the one in class at the end of April, I think. But this is for Form 1. How do you know if it's Form 1? Well, you take a look at your first page of your exam, and if it looks something like this, you're in business. If yours has the picture, with all like the woo, woo, woo stuff, yep, you have Form 2. So this is form number 1. Basically, here, let me hop back here for a second. Let's see what happens if I do that. Cool. Okay. Basically, I'm going to go through this. Most of what you're going to see is the exam, occasionally the reference table. But I'm going to go through, I'm going to give you the ideas and the concepts behind every question, kind of just going through it as a thought process. It's not going to be too in-depth, but if you have questions, mark them down on your exam, come see me, and we can go through that. Hopefully I don't make any mistakes because I'm a little tired, but we'll see what happens. So what are you going to need? You're going to need your test and you're going to need your reference table. If you don't have those out, maybe pause this video and go get those, and a calculator, maybe something to write with, all that crazy stuff, and then restart the video and we'll go from there. I'll just grab a quick drink. Okay, so let's see here. Let's go. Oh, sorry. Let's switch to the iPad. So you can see the exam, and we'll skip down here and we'll start with the multiple choice. Now, the catch you're going to see is the way this scanned over, it didn't block out any of the questions that you didn't have to do. So what I did, you'll see as we go through them, I X'd them out on mine just so that we know. So let's see here. First, we'll make sure that my ink is, yep, that'll work. Okay. So the modern model of the atom is based on the work of, well, it wasn't one scientist. It was lots of scientists. And it was over a long period of time, right? We went from, let's see, solid spheres with Dalton to stayed with solid spheres, but we had the plum pudding model with Thomson. Then Rutherford really changed the game with empty space, and then the Bohr model, and then quantum mechanics with Max Planck and Planck and all those guys. So yeah. Number 2, which statement is true about the charges assigned to both an electron and a proton? Well, I know protons are positive and electrons are negative. So 1 is out, electron is positive, 2 is out, and I know 4 is out because they're not the same. So yeah, number 3. Ta-da! Oops. Number 3, and so this is kind of how it's going to go, right? In a wave mechanical model, an orbital, okay, it's a region of space in the atom where there is, that's where you're going to find electrons. So as I look, this question, just, so you think about it, it's based on high probability and circular path, and then you have electrons and you have neutrons. So this is one of those like truth table questions, but here's the deal. It's an orbital. It's not a circular path. That's an orbit, right? And it's where you're going to find electrons, right? The wave mechanical model, it's the newest model. It's based on orbitals, which are probability regions of electrons. It's where you're going to find electrons. Excellent. Okay, question 4. This one I'm going to have to go to my reference table, and I'm thinking about the periodic table in general here. So the key to this oxygen, this 17 number, that's the mass number, which is the number up top. And when I look, the atomic number, of oxygen is 8. So what? If I want to know the charge of the nucleus, in the nucleus are protons and neutrons. Neutrons don't have a charge. Protons, which is what this bottom number tells you, that's a P, that's in the nucleus. So I have 8 of them. They're positively charged. It's going to be positive 8. The nucleus is, even though it's an atom, here, sorry, let me change ink here for a second. No, ink. There we go. An atom is neutral, but the nucleus of the atom is not neutral. The -2 is the ion that it can take on. That doesn't work. And then 17 is just like, hey, let's see if they don't know anything about it. So that's what this question was really looking at, right? Number 5, which pair of symbols represents a metalloid and a noble gas? So yeah, group 18, right? That doesn't work. And that doesn't work because neither of those have a noble gas in them. So the noble gas is going to be argon. Neon and xenon are both noble gases, so that doesn't work. So AS, arsenic is a metalloid. It's a semi-metal. It's on the staircase. So you just had to look at your periodic table and figure that one out. Chemical property of iron, flattened into sheets, that does not make something new. Conducting heat and electricity, that does not make something new. Combines with oxygen to form rust. I like that one. I'm going to keep that one around. Drawn into a wire, that does not make something new. Chemical properties make things that are new. So it's got to be choice 3 because that's the only thing when you make something new. Question 7. Okay, this is not meant to be difficult, right? The mole ratio between nitrogen gas, which is right here, and hydrogen gas, which is right here. It's 1 to 3. So boom. The only time I've seen it a little more complicated is when it was maybe like 2 to 6, and then it would come down to 1 to 3. So that was, but otherwise those are just like straightforward, find it and go. Okay, so now with 8, I'm going to zoom in and change my ink size because I'm going to need to write a little smaller. So the percent by mass of oxygen in this thing. Well, first off, I need to find out how much this whole thing weighs. And just so happens I have my handy dandy calculator of science. So let's turn that on and let's see. We got, really when I look at this thing, it's C3, right? Because there's 1, 2, 3. Sorry, 3. H is, you got 3 and 2 make 5 and 1 makes 6. And then O. So if I do the math for that, that's going to be carbon is 12 times 3 plus hydrogen is 1 times 6 plus oxygen is 16, so times 1. That's a total of 58. So now if I want the percent mass of oxygen, well, oxygen takes up a total mass of 16 because there's just one of them. So it's going to be 16 divided by 58 times 100. And I know it's not going to be 10%. That's too easy. Let's see, half of 50 is 20. It's not over half, so it's one of those two. So 16 divided by, 58 is 27. So, yep, choice 2, whammo. You know what? Let's keep zoomed in here. I think I like this better. But I'm going to make this just a little bit bigger and see how that works. Okay, so cool. Number 9, covalent bonds are formed when electrons are not transferred. That's ionic. And captured by the nucleus, nope, that is, we're going to learn about that later. That's called electron capture, believe it or not. It's a type of nuclear decay. It's, what the heck is it? Oh, positron, yeah. Mobile within a metal, nope, that would be metallic bonds. Ah, yes, caring is sharing, and sharing is caring. Sharing is caring. Caring starts with a C, so does covalent. Choice 4, right? Because covalent bonds are shared. Oh boy, number 10. Okay, so maybe you forgot my little trick with this, and I'll get to that in just a second. But maybe you remember SNAP, right? So symmetric is nonpolar and asymmetric is polar. So let's see, polar is symmetric. No, that doesn't make sense. Polar is asymmetric. Yeah, that's what that says. Nonpolar is symmetric. Yeah, that's what that says. So that makes sense. I'll keep those two around. Nonpolar is asymmetric. Nope, doesn't make sense. So now at least it's a 50-50 shot, right? And what you got going on here, the little trick, is if you remember, carbon can form 4 bonds. Boom, it has 4 valence electrons. It likes to form 4 bonds. And if it's surrounded by 4 of the same thing, no matter what those things are, it's going to be a non-polar molecule because they're all pulling the same. You're not going to get that whole opposite ends with opposite charges type thing. So sweet. Let's see. Which change occurs when barium loses 2 electrons? Well, let's see. Electrons are negative, right? So if I lose electrons, I should get more positive. So let's see. It becomes negative. No. Becomes negative, no. It becomes positive, yes. It becomes positive, yes. And now, anytime you lose electrons. It's just like if your wallet loses money, you're going to get smaller. So that means the correct choice is number 3. That becomes a positive ion and its radius decreases. Da-da-da-da. Okay, next page. Cool. Conductivity in metals results from the metals having, oh boy. Well, there could be a lot of different things here, and I might have to look them up, but I definitely know that number 3 is not true. The protons don't move in the nucleus. Like, that's bogus. The electrons do move in the valence shell. I like that. As far as the electronegativity and ionization energy, these things go hand in hand. So they're either both high or they're both low. The catch is metals, they're low, right? Electronegativity is how well you hold on to electrons, and metals don't hold on to their electrons. You could look those values up too and see that they're both small. So those don't make any sense at all. It's definitely number 4, which is what I was leaning to. But there you go. Sweet. 13. Hey, least attraction for electrons. That's all about electronegativity. I want to know which one is the least electronegative. Ooh, okay. That's the catch, right? Least. Usually it says most. So I'm looking for the thing that is farthest away from fluorine or has the biggest value. Well, fluorine's not going to be it. It's the strongest. Oxygen is right next to it. Nitrogen is a little bit farther away, and then chlorine is one away. So I'm going to go with nitrogen without looking this up because it's the farthest from fluorine, which is the most electronegative. But I'm willing to bet if I look it up, I'd be right. So cool. Recovering a salt mixture. Oh, we've talked about this, right? You could do evaporation. Filtration is not going to work because the salt and the water will just go right through the filter paper. Paper chromatography, that's what we did with the markers in that one lab with the coffee filters. So that's not going to help you get the salt back. And density determination, no. That could tell you like how much salt is there theoretically if you know what the salt is, but it's not going to help it get back. So yeah, number 1 is definitely the right answer. If you notice when I go through these, I still check to see if the other answers make sense or not. If the first one seems right, just check the other ones to make sure, because if you end up with 2 that are right, you're doing something wrong. So 15. Average kinetic. Oh, okay. Average kinetic energy is the same as temperature. So if I want the greatest, I want the highest temperature. It does not matter how big the sample is, which means number 2. It's got the highest temperature. Bada boom. 16. Helium is most likely to behave. Sometimes they've done it as least likely, so you got to watch out. Ooh, ideal gas, right? Ideal relationship. Low pressure and hot. So whammo right there. Because think about it. High pressure, if you pressurize a gas, you're going to get a liquid. And as far as temperature, low temperature doesn't make any sense because you're not going to find gases at low temperatures. You're going to find them at high temperatures. So, but again, an ideal gas is like an ideal relationship. It's hot and low pressure. So number 3. Boom. 17. Let's see. Element oxygen, O2 and O3. So I can tell you right now, these are what are called allotropes, in case that word comes up. Allotrope. All right? It's the same element taking on different forms. So let's see. These 2 forms of the element have, well, oh, okay. So this is chemical and physical properties. Huh. Okay. So they're probably either both going to be the same or they're both going to be different. I don't think it's going to be one same, one different. And I really, 4. They're definitely going to have different chemical properties. I can tell you that because like oxygen is, okay for us to breathe. But if you breathe ozone, you're going to have asthmatic fits and die. That's why we want ozone way up in the atmosphere and not down on the surface of the Earth. Physical properties, they definitely behave differently. So yeah, they're different. Sweet. Okay. Oh, right. This is an easy one. This jumps out immediately. Only because if the particles are in rigid, which means they don't move, fixed, which means they don't move, geometric pattern, the only way you can have particles in a fixed pattern that's geometrically like repeating and not going anywhere is if they're not moving and if they're a solid, right? Aqueous means it's dissolved in water. They're going to be floating all around. Gas, they're flying around. Liquid, they're able to move around. It's all about the solid. 19. Okay. Why does the powdered zinc make it go faster? More surface area, right? You're not really lowering the kinetic energy because that would be like making them move less, and that's not what's going on. You're not lowering the concentration because they're both 5 gram samples. It's the same amount, and there's not more zinc atoms because it's the same amount of stuff. You're just increasing the surface area. So definitely choice 3. 20. Oh, equilibrium. Okay, this is what we talked about with the fish tanks, right? And awesome. They said the rate for each one. That makes this kind of easy. The rates have to be the same, right? So it's choice 3 because let's see. Let's just make sure. The forward number 1, right? The forward reaction is less than the reverse. No, they have to be the same. Forward reaction is greater. Nope, they got to be the same. Forward reaction stops and the reverse reaction continues. No. Definitely number 3. The rates are the same. The concentrations remain constant. 21. Oh, catalyst, right? Catalysts increase the rate. This is why I asked you guys this all the time. Increases the rate of a chemical reaction by lowering the activation energy. It doesn't lower the potential energy of the products because remember, right? If you got like curve number 1, catalyst will do like whoo. Whoops, that was a bad example. Let's try that again. Woo! Still a bad example, but you get the idea. The level of the products doesn't change. The level of the reactants doesn't change. It's the activation energy that changes. So yeah, it doesn't raise the temperature and it doesn't raise the concentration. It lowers the activation energy. Okay, let's see. I don't think there's any on this page. Nope. So that takes us through part A. You noticed, I think we looked at the reference tables like twice on part A. Part A is a whole lot of kind of general knowledge and what do you know about chemistry? Excuse me, a little drink of water. Part B1, however, now we're going to be busting out the reference tables quite a bit. So you might notice that I flip back and forth between some different things. Like I go to the reference tables and actually show you what they look like. So let's deal with this here. Which simple symbol represents a particle that has the same total number of electrons as sulfur 2 minus? Oh, crapacola. There's a couple different ways that you could do this. Let's take a look here. It's going to whoops. Didn't mean to do. Hi, how you doing? Reference table. There we go. Boop, 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 boop. Too far. And let's just rotate this view. Doink. Okay. So, boop, 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 boop. So here's sulfur, right? And it says it's 2. Yeah, you get the idea. 286. So let's go to the hand. That's what I want. There we go. 286. So if it's 2 minus, here's where it gets a little complicated. That means that it picks up 2 electrons. So I'm looking for something that's 288. Okay. Now, here's one thing that you can do. If this gains 2 electrons, right, it goes bump, bump, and becomes argon, which happens to be one of the choices, number 4. So that's the correct answer. I'm going to circle it now. You'll see it later. But here's what I'll do, right? We'll make your life a little easier. So the answer that we're looking for is 288. Argon is 288. Oxygen with a 2 minus would become 28. Sorry, I'm writing this. It would become 28. But you can see if I were to go bonk, bonk, it becomes neon, and that's not what I want. Si is way the heck over here. That's if you go the wrong way, right? 1, 2. But that's 2, 8, 4. That doesn't make any sense. And Se is 1, 2. That's krypton, which is, I'm not even going to bother writing that. 2, 8, 18, 8. All right. But if you notice the answers that it gave you, it was, oxygen. Number 1 was oxygen 2 minus, dunk, dunk, neon. Then it was silicon, which is if you went the wrong way, dunk, dunk, 2. Then it was Se2 minus, dunk, dunk, which was wrong. Then it was argon, which is what you wanted, dunk, dunk, right? That's what we said. So let's do this, and then you're going to see my ugly mug again. Hi. And there's the sheet again, right? So that's what that one was all about. You just had to match up the reference tables. It was a little tricky, but definitely doable. So cool. Okay. Come on. Nope. Undo. There we go. Zoom. There we go. Data table below shows X, 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 Y. So these are all different elements. They didn't tell me what they are. Let's make that a little bigger. Oh, okay. So from the same group, see, you got to read the instructions sometimes, right? So if they're in the same group, that means we're like moving down the table. And I know as I move down the table, it should get bigger. And I'm seeing that with the mass, it's getting bigger. So basically, I'm looking for a radius that falls between 141 and 171, which is 166, right? 103 is out here. 127 is out here. 166 is in there. And then 185 is out here. So yeah, dude, number 3. Like, pretty straightforward. 36. Oh, man, I'm missing my thumb or something. There we go. Which substance has a chemical formula with the same ratio of metal to nonmetal as... Oh, boy, this is cool. Okay, so there's a couple different ways you could do this. You could, and I would say you could figure out that potassium sulfide is not Ks because K is +1 and S is -2. So it's really K2S, right? But potassium is in group 1 and sulfur is in, I'm not going to have the room, group what, 16? Yeah, 16. So you just have to find 2 answers that have that because they'll have the same charges, right? And that'll end up giving you the same ratio. So sodium is in group 1. That's good. Oxygen is in group 16. I like that. Chlorine is in group 17. So that's not going to work. And magnesium is in group 2. So that's not going to work. Yeah, so definitely choice 1. Right? Because if I clean this up a little bit, right, we wanted K2S. And if you work the charges, sodium oxide is going to be Na2O, right? +1 -2. Sodium chloride, you know, is NaCl. That's a 1-to-1 ratio, not what I want. Magnesium chloride is magnesium oxide is MgO, again, 1-to-1, not what I want. Magnesium chloride is MgCl2. That's 1-to-2. Not what I want. I want 2-to-1. So choice 4. 37. Molecular formula for glucose is that. Empirical formula, lowest whole number ratio. So when I reduce this, right, 1 to 2 to 1. So choice 2. It's got to be just the reduced formula is all. Reference table F. I can do this in my head. But if you want to get out your reference tables and open them to table F, this will help you. So here's what I'm looking at, right? Let me bust out the old highlighter. A little too big. Let's go with that one. So those are not the answers because potassium in choices 1 and 2, that's in group 1 and it's always soluble with no exceptions. Nitrate, NO3, in number 4, that's always soluble with no exceptions. So we're dealing with, right, soluble, soluble, soluble. This must be insoluble, which is what they're asking me. So I'm going to take a gamble that, why don't I just check? Even though I know that's the right answer, let's just go take a quick look at table F. But yep, PO4. Okay, so phosphate is insoluble and calcium is not one of the exceptions. So bingo bango. 39. Sample containing only magnesium chloride. Components. Oh. Okay. So I bet if you got this one wrong, it's because you figured out the mass of chlorine because they gave you the percentage chlorine, right? So if it's 74.5%, the remaining, why am I sucking at math? 25.5, right? 25.5% is magnesium. Let me just double check that because I'm feeling kind of stupid. 24, 74.5. Yeah, I'm good. So if I take my 190.2 and multiply it by 0.255, that's going to give me my answer. So let's see. Times 190.2. Ooh, no, that doesn't work. Times 0.255. 48 something. Yep, there you go. Boom, number two. Like I said, it's I could kind of eyeball the math, but I'm willing to bet if you got this one wrong, it's just because you missed that this was chlorine and they wanted to know about magnesium, right? But that's what's going on with that one. 40. Which molecule contains a nonpolar covalent bond? They're all nonmetals, so that takes that one out, and it's going to be choice three. And that's because to be non-polar, it has to be between the same two elements. In every other case, like in number one, you have C to O, and then again, C to O. Here it's C to O. Here in each case going out, it's C to Cl. They're all different. To be non-polar, they have to be the same two nonmetals. So it's choice three. Because again, it wants bond, not molecule. And the way you could know that is because when you look at the molecules, 1, 3, and 4 are all nonpolar, right? Because it's the way they work. CO2 is nonpolar. Sorry, didn't mean to do that. CO2 is nonpolar. Again, you have carbon here surrounded by 4 of the same things. It's going to be nonpolar, but it didn't ask about a molecule. It asked about a bond. So choice 3. Yep, definitely gonna have to bust out the reference tables for this one. According to reference table G, unsaturated when 80 grams of the substance dissolves in 100 grams of water. Right, we said that's important. So let's go take a look at table G here real quick. So where are my reference tables? There we go. Zoom out, and we're gonna have to rotate this puppy again, counterclockwise, and up we go. Table G, not far enough. Boom. Okay, so let's see if I can do this from here. Yep, good. So I got 80 grams of stuff right here, 10 degrees Celsius. That's that point right there. Hopefully that car alarm stops and you don't hear it. And hopefully it's not my car alarm. Nope. Good. There we go. Sorry about that. So if I want to know which one is unsaturated, that point has to be below the line. And I actually already know the answer to this. It's going to be number one, because when you look, right, Ki is like stupidly soluble, but 80 at 10 is definitely below that line, which is unsaturated. For KNO3, which is this curve right here, that is above the line. That's super saturated. For NaNO3, it's pretty much right on the line, which is saturated. And NaCl, it's above the line, which is super saturated. So again, you're going to see me. Hello. No, there. It's choice one. It's Ki. Right? Okie dokie. So here, there's the right way and there's the wrong way to do this. Unfortunately, if you do it the wrong way, you still get the right answer, which really irritates me. But it wants to know parts per million. So that's the part divided by the whole times a million. Now, I'm willing to bet that you all did it as 0.02 over 1,000 times 1 million, which is great. But technically speaking, this is just the water. To get the grams of solution, which is what the question wants, you have to also include, I lost my pointer. Come back. Good. You got to include this mass too, so 0.02, right? And it actually, like I say, it doesn't change the answer because your answer, my back, your answer will still round to the same thing, whether you include that 0.02 or not. But like I say, there's the right way and there's the wrong way to do things. So let's see, 1, 2, 3, 4, 5, 6. I'm coming up with 20, right? Because if you do it the correct way, it's 19.999600001, which significant figures goes to 20. So choice 1. Cool. That's that page. Moving on. Got to zoom out a little bit here. 42 two, which is, okay, two elements, and it's saying that's one thing, that's the other. Choice one is not two elements, it's just one. Wait a second, did I do this right? Hang on, timeout. See, I didn't read all the instructions. So those are elements. Okay, that's good. Which particle diagram represents molecules of only one compound? Okay, so one is still out because a compound is going to have to show both of these things bonded together because it has to be two or more different elements and everything has to be the same. So I'm leaning towards three is going to be my answer. Two does not work because this is one element and this is another. So that's a mixture of elements. And four doesn't work. Whoops, I'm sorry. Four doesn't work because even though you have things bonded, let's do some highlighting. Boom, boom, boom. Those are one compound, and boom, boom, boom. Those are another compound. So I only want one compound. Got to be choice three. Again, a compound is two or more different elements bonded together. And if it's one compound, every single of the molecules looks the same. Sorry, had to get a little drink of water there. Okie dokie. Oh, sweet. So again, this is one of those wordy questions, and so is the next one. But 44, you can either tackle the endothermic side or the exothermic side, or the entropy increasing or decreasing. I don't know. I'm thinking here's energy, right? Boom, boom. Energy has to go in. So that means it's endothermic, it's a reactant. So it's got to be one or two. And as far as entropy goes, you start with one thing and you end with two things. That is definitely increasing the entropy. Things are getting crazier through that process. And remember, when it comes to that stuff, nature likes lazy and crazy. For question 45, a 1 gram piece of zinc reacts with 5 milliliters of HCl. Okay, so I want it to go with fastest, right? So I want the highest concentration, because that's one thing I'm dealing with, and I want the highest temperature, which is choice 4, because 1 is definitely less than 2, and 20 is less than 40. So, yep, choice number 4. 46, okay. At STP, fluorine is a gas and iodine is a solid. Oh, this is totally going to help you out. Is it? I don't know. But the solid versus a gas, it's all about the intermolecular forces, right? Because if it's at STP, their average kinetic energy is the same, right? Because average kinetic energy is the same as temperature. So these are out. Now the question is, it says fluorine is a gas. That means it's held together weaker than iodine, which is a solid. So it's saying here fluorine has, yes, weaker forces of attraction than iodine because fluorine is a gas. It's held together weaker. So definitely choice 1. Awesome. Okay, so that is the end of B1. I'm going to grab another drink here. B1, you saw definitely more reference table based. Now we're going to get into B2, which is short answer stuff, right? So let me just grab this drink here real quick. But we're more than halfway through the test, so that's good. Again, if you have any questions with this as you're going through, just mark them in your exam and come see me. Hopefully I don't make any mistakes, and I haven't made any mistakes, I hope. But we can clear them up if we do. And it looks like I got to get cooking because I got 30% battery left on my iPad. Well, 37. But anyway, so with some of these, I'm probably going to talk through them more than I'm going to write stuff because it'll just take too long to write stuff. But I'll write when necessary. So let's get cooking here. Number 51, what type of reaction does this represent? This is totally decomposition. I start with one thing and it's breaking apart into its pieces. So it is definitely decomposition. Synthesis would be if I was making things. Chemical reaction really doesn't work. Technically, you could get away with saying endothermic, which is bonkers because it didn't talk about energy anywhere. But it is an endothermic reaction, so that works. Technically speaking, it is also a redox reaction, but we haven't talked about redox. But decomposition is what you really should have gone for. This one gave you a lot of trouble. How does this balanced chemical equation show the law of conservation of mass? It's actually not that difficult. You start with a total of 4 H's and you end with 4 H's. you start with two O's and you end with two O's. So you start and end with the same number of atoms. That's how it shows the conservation of mass. Just simply saying that mass was neither gained nor lost, that just kind of states the conservation of mass law. It doesn't show how this equation shows that. Right? So you got to make sure that you're referencing it back to the equation, and then it's that you start and end with the same number of elements, the same number of atoms, something like that. We'll erase this because it'll be nicer. Question 53: total number of moles of O2 produced when 8 moles of water, are completely consumed. Well, it's a 2-to-1 ratio, right? So to go from 2 to 8, I have to multiply by 4. So since there's a 1 here now, I'm going to multiply by 4, and that means the answer is 4. You could also do it this way. You could say 8. Let's make that a little smaller. 8 moles of water. 2 mole. Is that right? Yeah. Yeah, sorry. Water is 1 mole oxygen. That lets my waters cancel, and I'm left with 8 divided by 2, which is 4. It's the same thing I said before, right? So no biggie, not too bad. But there you go. So that was those ones, and let's see, we're doing a whole lot of skipping here. Oh boy, oh boy, oh boy, oh boy, oh boy, these ones. Erase that. There we go. Okay, so check it, right? In terms of atomic particles, we're talking about protons, neutrons, and electrons, right? State one difference between these 3 isotopes. They have a different number of neutrons, right? If you say, oh, they have a different mass, that's not atomic particles. Oh, they have a different natural abundance. That's not in terms of atomic particles. You're wasting my time if you say that, right? You got to answer the way the question's wording it. If you're just grasping at straws, you can do better than that. Isotopes, it's the same element, same number of protons, different number of neutrons. That's what you needed for 59. They have a different number of neutrons. That's it. 60, based on the natural abundances on the data table and the space provided, show the correct numerical setup for calculating the average atomic mass. Ugh. So, I don't know why I keep there. Let's see here. Oh, this is so annoying. This stupid Zoom function is not working. All right. Let's get some small ink going. So here's what we got to do, right? We got to take the masses and we got to take the abundances. You can't just average the masses because they're not all in even abundance. So you have to take the first mass, which is 19.99, and multiply it by its percent, 90.9. And then you're going to add that to the next mass, which is 20.99. Multiply that by its percent, 0.3, and then you're going to add that to the final mass, which is 21.99, and multiply it by its percent, 8.8. Divide the whole shebang by 100. Now, that's just one way to do it. You could also skip the dividing by 100 and just divide each of your percents by 100. So you'd have like 19.99 times 0.909 plus 20.99 times 0.003 plus 21.99 times 0.088. But you got to be careful moving the decimal point with that. That's why I like doing it this way, but whatever way works for you. But it's an average, it's a weighted average, so that's how you have to solve for it. You have to use that formula. Sweet. 61, based on the natural abundances, the average atomic mass is closest to which whole number? Well, if you did the answer, like if you actually did this math, you'd get that number. But take a look. You have the most of that one, which is the closest to 20, right? The reason they did that is because when you have 20, 21, and 22. If you just do a straight average, your answer is going to come out as 21. But when you take into account the percent natural abundance, the answer should come out closest to 20. That's why they did that question. So just throwing it out there for you. 62, explain, oh, hey, two answers, right? Why they have similar properties? Same group, same number, valence, electrons. Because this says based on the periodic table. So either of those answers would work out okay. That's group. But I just say, get in the habit of when it says explain why these two elements have similar chemical properties, just say both, because no matter how they answer it, you'll be okay. All right, so that turns into what I call a regurgitation question. You just know it and just blah, say the answer. Okay, cool. Hey, look at that. We're on to question C. That's exciting. 65. Oh my goodness, 65. So this was Rutherford, and something just happened. I don't know what just happened. Oh, I got an text. Okay, cool. Sorry. So two conclusions from the atom. One, empty space. Like that, you need to know that. Plain and simply, you need to know that. Rutherford, empty space. Boom. What else did he say? So since this should have been a 1 point, or I'm sorry, it should have been a 2 point question, but I only made it 1 point, so I was a little lenient with what the other thing was. But there's a nucleus, electrons spin around the outside, and there's a dense positively charged nucleus in the center. Those were really the two big findings that have to deal with structure, is that atoms were mostly made of empty space, and there was a positively charged dense nucleus in the center, which is where most of the mass was. So that's what 65 was all about. 60, oh God, I have to graph, really? Okay. Give me a second. I hate graphing. Because I got to pull this up on another computer so I can see my data while I'm doing this. Oh, you know what? I got a better way to do this. Yeah, I totally got a better way to do this. Hang on. I'll bring it back here. Where is it? Where did I just find that? Please hold while we're having technical difficulties. There it is. Okay. Yeah, boom, right there. Okay, you want to see what your answer should look like? Where am I? There we go. It should look like that. Boom! It's that simple. You needed to set up, what did I ask you to do? For 66, you had to set up an appropriate scale. So that's all. Oh, wait, you can't see what I'm doing. Where are you? There we are. That's this part right here. Setting up a scale that let me see the trend. Basically, I had to be able to see that it went up, and then it flattened, and then it went up again. Pretty straightforward. 67, plot the data. Oh, it's getting late. Plot the data and circle and connect the points. So basically, that's what it should look like. Not too complicated. I think so. 68 says, oh my goodness, let's see, back up there. 68 says, based on the data table, what's the melting point? Well, you kind of need to see what the data table says, right? Right here. There we go. So take a look at the data table, right? The melting point is a phase change. That means that the temperature should stay the same. And right about there, oops, I missed. It stays the same. So the melting point is 53. There's really no negotiation on that one. For question 69, what's the evidence that the average kinetic energy of the particles of the substance is increasing in the first 3 minutes? Well, let's take a look. In the first 3 minutes, what happens? Oh, wait, I know. Average kinetic energy is the same as temperature. So the temperature increases. Ta-da! 70. Okay, so heat of fusion. This is right, like, dude, like, Q equals MHF, right? It's screaming that to you. So how many joules of heat are needed to melt 7.5 grams at its melting point? So Q equals the mass, which is 750 grams, times the heat of fusion, which is 122 joules per gram, because you couldn't use 334. They gave you the value here, and that's going to come out to be some number. I want to say 915. Yeah, 915 joules. And really, that question should look familiar because you've seen it on an exam kind of recently. Ha, ha, ha. Okay, didn't have to do those, didn't have to do those. Here we go. 77. So this is a question where when this was asked on a Regents exam, I thought it was really, really tough because I thought you were going to have to do all this crazy math based on these numbers, which you're not even supposed to know how to do that math. But that's because I didn't read the question. And it says right here, cylinder A contains 22 grams of CO2. So if I take my 22 grams and I know that 1 mole is 44 grams. Let me just double check that. All of a sudden, I'm having a bit of a brain fart because carbon is 12 plus oxygen is 16 times 2 is 32 is definitely 44. Yeah, there's a reason they did that. It makes the math easy. It's 0.5. That's sloppy. 0.5. It's half a mole, right? But you had to know up here that it was 22 grams. So, 78. Sorry. Explain why the number of molecules in N2 is the same as the number of molecules in cylinder A. Right here. It's Avogadro's law, right? They're two gases at the same conditions, same volume, same pressure, same temperature. And that's what Avogadro's law states, is when you have that going on, you'll have the same number of molecules. Ta-da. 79. Okay, so this is just a gas law problem, right? P1 V1 over T1 equals P2 V2 over T2. So it wants us to calculate the new pressure. So, well, let's see. Pressure is at 1 atm to start. The volume is 12.3 liters. And the temperature is 300 K equals, okay, it's saying I want to know the new pressure at, the volume is still 12.3 because it didn't change. And it even says the volume remains constant. And the new temperature is 450. Okay, so that's one possible answer. You didn't, since the volume doesn't change, you don't really have to have the volume here. You could just have that too, right? That's totally fine. So since this was just the setup, with or without the volume, that's what you want to have. Ta-da! Oh yeah, here we go. Okay, so you guys did not like this, but it's totally a fair question. So state the trend in the boiling point of the hydrocarbons contained in the crude oil and the number of carbon atoms in these molecules. Look, they tell you how many carbon atoms are here, and they tell you the freaking boiling points. So what's the trend? Well, let's see. Less carbons, lower boiling point. More carbons, higher boiling point. That's the trend. The less carbon atoms you have, the lower the boiling point. Or the more carbon atoms you have, the higher the boiling point. Or as the number of carbon atoms increases, so does the boiling point. As the number of carbon atoms decreases, so does the boiling point. Direct, right? So describe the relationship between the strengths of the intermolecular forces and the number of carbon atoms. Well, since their boiling point goes up, that means you have to put more and more energy in as you move down to get them to separate. So as a result, the intermolecular forces are increasing when you have more carbon atoms, right? And that's just a direct story, and that's the last question. So let me get out of here. Yeah, that's just a straightforward thing. If you because there's more carbon atoms, there's a higher boiling point. The reason there's a higher boiling point is because the forces are holding them together stronger. They're bigger things, and because they're bigger, they're able to be held together stronger. In the case of these van der Waals forces, which you don't necessarily know that, but that part doesn't matter. You can just tell higher boiling point, stronger forces, because you have to put in more energy to overcome it. So there you go. That's going through this exam. I hope that helped. Again, if you have any questions, please feel free to come see me, and I can help sort those out. Otherwise, I hope to see you on June 2nd at noon for the makeup exam. There'll be a survey coming out on Drive and Schoology and Twitter and Facebook and all that stuff to RSVP if you're going to be there, to make sure that I have a copy of the exam for you. If you don't take that survey, I cannot guarantee you're going to have an exam. In fact, I can just about guarantee you're not going to have an exam. So take the survey. But again, the makeup is June 2nd. So if you have any questions between now and then, please feel free to come see me. Otherwise, if you are taking the Common Core exam, you can just stay and take the makeup. If you're not taking the Common Core exam, you need your own ride in to school in the afternoon to take the exam. There will be buses at, I think there's the 2:30, 3:30, and 5:30 buses that'll be running that day. So you'll be able to get home if you need to. But other than that, thanks for watching. I hope this helped. And yep, I am out of here. Have a good one, everybody. Bye-bye.